Hello, everyone. This is the map.h SI pre-recorded session. I didn't get to map.h in the last session, unfortunately, so I'm going to go ahead and cover this now because the project's due in a couple of days, and I didn't want to keep you guys waiting. So if you're watching this now, thanks for watching it. It's going to be a pretty short video. We're just covering the map.h ADT. So if you watched the previous video we made, it's talking about the driver for the project. We go pretty in-depth into what maps are there, so if you haven't watched that, go ahead and watch this one first. This should concentrate further on like how to actually implement the functions for the map.h class. So we can go ahead and get started. I kind of first want to get some intuition behind like what map.h actually is. So essentially a map, I want to stress this a lot during this presentation. So basically a map is just a binary search tree under the hood. So remember a binary search tree, we had these nodes and we had the left and right pointer and stuff, and we had values associated with these nodes. All a map is the binary search tree of a pair. So a pair is declared like this. And what a pair means is that two numbers or two types are associated. I had a pair of string int like this, and I'll call this example like that. I can set the string bit to be euchre and the second bit to be 5. So what I did here is I created a pair so that if I access example that first, I get euchre, and example that second, I get the number 5. What a map does is a map is a key value pair. So it's very similar to a pair. What happens here is that we have some type for our key, and we have some type for our value. Every key must be unique. This is sort of like in our binary search tree. If we just had integers, we couldn't have 5 in our binary search tree twice, right? We can't have repeats. And the exact same holds for our keys. So what a binary search tree is, it's a binary search tree of pairs where we sort it according to the key value. So let's say, for example, I'll make this pretty simple. Let's say I had a binary search tree of pairs, and our pair type was integers to strings. And I had some pairs like 5p4 as our string right there, and I had like 3 euchre and 7 EECS. If I were to go ahead and insert these into the tree in this order, I would go ahead and first make 5p4 my root. So go ahead and put this 5p4. The next thing I insert is this 3 comma euchre. Remember, we're going to sort this binary search tree according to the key value, not the value. It's kind of redundant, but yeah, we only want to sort according to our key value. The value of our key is kind of relevant here, right? We're concerned with finding the key and putting it into our binary search tree. So 3 is less than 5, so we go ahead and put our 3 euchre here, like that. And then 7 would go right here, equals 280. Let's put 280 string. So I hope that makes sense. So we're basically creating a binary search tree of pairs. So a map is a collection of pairs. And again, every single key has to be unique here. Whenever we insert into a binary search tree of pairs, we have to make sure that we are inserting a unique element or finding a unique element. The values are kind of relevant, right? Like it doesn't matter if this value and this value are both the exact same. What matters here is that our key types, or our key values, are unique. Okay, cool. Let's go ahead and get out of that. And yeah, so values can't be repeated again. So the key value is the key. I'll just keep saying that. The key is what matters. The key is how we sort our binary search tree, and the key is also how we find elements in our binary search tree. So if we wanted to say, does this value exist, or does this key exist, we would just search for the key that way. If you want to search for a key in a binary search tree, you would just access the type of that node and do dot first, and that would give you the key. If you want to get the value, this text in green right here, if you want to get that, you would go ahead and access dot second. For most of this project, you're probably going to be accessing dot first because we're concerned with the keys. But if you had to access the value for some reason, you'd want to use dot second. So again, if you're looking at a binary search tree and you want to find the key of that node, you would just access dot first. And you should be sorting your binary search tree according to the key type and the value of its key. So going on to this, the first thing you have to do is create a custom comparator. So remember that we're sorting our binary search tree according to our key type. So whatever our key type is, we have to write a comparator for it. So let's say, for example, our key type was an integer. We would sort these according to integers, where everything to the left of our root would be less than, everything to the right would be greater than, in terms of integers. But we have to create this abstractly for every key type. So we have this class pair comparator to accomplish this. We need to do two things. We have to go ahead and create a custom constructor that's going to take in some comparator, and we also need to override the operator like this to take in two pair type objects and compare them. Remember, this is going to help us sort our binary search tree according to the pair types. Here's the thing though, we're only concerned with the keys and not the values. So if you're comparing two pair types, we're only concerned with the dot first of those types. The dot second is kind of irrelevant. That's the value of our key value pair. We don't really care about that. For sorting a binary search tree, we only care about the key of our pair. So in this section for custom comparators, you should be going ahead and creating a custom constructor that takes in some comparator, and you want to set it for that pair comparator class. And then you also want to override the comparison operator, which would essentially look like comparing two pair types and returning true or false if one of them is greater than the other. And that'll help you sort your binary search tree. Okay, so going further into this, here's the big thing about this. Most of these functions that you have to accomplish for map.h, you've already written for binary search tree. Because all your map is it's quite literally just a new binary search tree. So whenever you go ahead and create a new map, you're just making a binary search tree with two stipulations. Remember, our binary search tree had two components to it. It had some type of a node and the comparator we're using. So we were using less. We use that for binary search tree.h. But here, remember this? We just made some custom comparator over here. We just made this. So when we make a map, we need to be sure to create a new binary search tree and give it the type of pair comp, because remember, our type's going to be some key value pair, the key and the value, and that's pair comp. So that's pretty good. And then our comparator is just going to be whatever our custom comparator is going to be that we created in the last step. So that's basically all a map is, the binary search tree of type pair, where the dot first is going to be our key and dot second is going to be our value. And here's the cool thing. Since we've already done everything in binary search tree.h, let's say we want to find a key. We can quite literally just call dot find. We've already written that. Size, we already have dot size. Empty, we already have dot empty. So all these other functions you've already written, you can just copy these over. You don't have to copy them, you just call them, because you're working on a binary search tree. A map is just a binary search tree of type pair. The nodes are pairs instead of like integers or strings. And if you want to sort it, you want to be sure to go ahead and look at the dot first element. That's basically all a map is. It's just a binary search tree with a different type. So we can go ahead and go to the last major function of the binary search tree, of the map, sorry. And it's going to be the bracket operator. This is accessing. So essentially how this works is, if you watch the P5 driver video we made a couple days ago, let's say I had some map of string to ints, like this, and I'll call this example EX. If I did EX and I put in some string here, like euchre, what I expect to happen is I'll either get the value of this key, or if euchre does not exist in my map, I'll go ahead and create it. And it will return 0 because the default integer is 0 for a map. So what I expect to happen here is, if euchre exists in my map, I'll go ahead and return its value. If it doesn't exist, I'll go ahead and create euchre in my map, and I'll go ahead and return the default value, which you don't have to worry about in this project. It'll do it for you, but that's just what happens in the map ADT. So in this function, like I said before, we're basically supplying a key to our map, and we want to check, does that value exist? If it does exist, return the value. If it doesn't exist, go ahead and add it to our map. So again, we can use the .find operator because we already wrote that, right? We've already written .find for binary search tree. So we can literally just go ahead and .find our key. If it exists, cool. Remember how we had .first was our key and .second was our value? If we find it, we can just return .second of the iterator that .find returns. If it doesn't exist yet, we can go ahead and we can insert this into our tree. We can insert the key into our tree. So there's two steps here. One, if it exists, cool. Return .second of the iterator that .find returns. If it doesn't exist, we have to go ahead and call insert on the key. And that is pretty much it for this part of the project. Again, it's pretty small, so you should have about like 100-ish lines of code, but most of it's just RME and stuff. So it's not that much work, but definitely get started on this if you haven't, because it is kind of annoying to debug. The hardest part is probably the custom comparator, so I can just reiterate some stuff about this real quick. Everything onward, I'd recommend just thinking about like what you can use from your previous implementation of binary search tree, because you can reuse a lot of it. Again, you're operating on a binary search tree, so you can feel free to call those functions whenever you want. But yeah, going back to this, it's probably the most confusing part is the custom comparators. We have to create an overloaded operator to compare to pair type objects, because pair type is a custom type we defined. Remember, in a binary search tree, or for a map at least, we're sorting it based on key value. And we know that keys are .first of our pair type. So we want to go ahead and compare the .first of two different pair types and return accordingly. So remember how we defined .less? Actually, it's some good advice. Go ahead and look at how the instructors define .less, or sorry, the less comparator in binary search tree, and use similar logic for that when you define your comparator for pair type. And that should make a lot more sense then. And you also have to go ahead and create a, sorry, my internet cut out there. So you have to create, again, this overloaded operator to compare the .first of two different pair types. Again, look at less for that, so that should make a little bit more sense. But you want to essentially compare the .first of two different pair types. And then for the non-default constructor, you just want to take in a custom comparator and then set the custom comparator of that class. So you're doing two things there. You're creating an overloaded operator, and you're also going ahead and creating a default and non-default constructor. And that is about it for map.h. So if you guys have any questions, feel free to leave any comments or email me or something like that. And I hope to see you all for the final review session that we're hosting this upcoming Sunday. So yeah, good luck in the project, and yeah, see you guys soon.